Welcome to the 10th lecture of combinatorics, and in the last class we were looking at this problem, namely the permutations of multi-set, right. How many ways you can arrange n objects in a line, and these n objects are of k different types, and objects of the same type are indistinguishable. AI is the number of objects of type I, then the number of different arrangements is n factorial by a1 factorial, a2 factorial, ak factorial. So, we this n objects, it is n objects are seen as a multi-set. We saw how to write the multi-sets, right, that S equal to, right, A1 times type 1, A2 times type 2 and so on, AK times type K, right. So, the permutations, all the things in the multi-sets are made in an arranged in an ordered list, right. How many ways you can arrange it. The key point here is that at certain type, there are several of them, repetition number is what we call for the number of times that certain type comes, they are indistinguishable. For instance, they appear in say position number 10, 13 and 14. So, within this 10, 13 and 14 positions, if you arrange them a particular type, you will not make any change to the permutation. Earlier it was not like that, because when they were all different, any change would have made a difference. So, we see that the number can be counted this way. Now, we will, our plan in this class is to look at some examples. So, we start with this example. So, a quality controller has to visit one factory a day. In the next 8 days, she will visit each of 4 factories. The factory names are A, B, C and D, and each factory will be visited twice. The controller is free to choose the order in which she visits these factories, but the 2 visits to factory A cannot be on consecutive days. So, you should not visit factory A today and tomorrow kind of consecutively, right. So, how many different orders can the controller proceed? So, we want to count the number of ways she can do this, right, the order in which she can visit the factory. So, as such what are the things we are permuting, because see, she visits each factory 2 times. So, we can say factory A comes 2 times, factory B comes 2 times, factory C comes 2 times and factory D comes 2 times. This is the multi-set. So, we essentially are interested in some ordering of this sort, right, C, C, D, D, which means she first day she visits A, factory A, second day she visits factory B, third day she visits factory B, fourth day she again goes to factory A, the fifth day she is in factory C, sixth day she is in factory C, seventh day and eighth day she is in D. So, this is this kind of a listing is what we are looking for, right, the order in which she visited the factories, and therefore, this can be modeled as permuting a multi-set. Here the multi-set is this AA, BB, CC, DD. In our notation, it can be written as 2A, 2B, 2C and 2D. Okay, 2A, 2B, 2C, 2D. Now, we know the answer if there was no further restriction, because how many permutations are possible for this thing, this multi-set? That we already know, because the total the cardinality of the multiset is 2 plus 2 plus 2 plus 2 8. So, that is 8 factorial divided by 2 factorial into 2 factorial into 2 factorial into 2 factorial. So, this is by using the formula n factorial by n1 factorial into n2 factorial into nk factorial, because k is equal to 4 here, right, n1 equal to n2 equal to n3 equal to n4 equal to 2 here, and n equal to 8, 4 times 2. That is why it is 8 factorial divided by 2 factorial into 2 factorial into 2 factorial into 2 factorial. But this is not what we are told, we have further restriction, this is not what we want, we have further restriction. What is the further restriction? The controller, she is not supposed to visit factory A on consecutive days. Maybe after one visit the factory has to reset something, or there may be a technical reason why she cannot visit the factory on A on consecutive days. She has to give at least one gap. By we will use our subtraction principle here. We would rather find the number of ways she can visit such that the factory A is visited on consecutive days, and then minus it from the total being this, right, total being this. No, total is not this. Yeah, total is this, total being this, total number of ways to visit is this. But consecutive days, if so, for instance, now we restrict that she has to visit factory A on consecutive days. So, what we want is the other thing, but we will do this way and then minus it off, right. That means because it should a permutation of this sort is not allowed, right, because A and A are not consecutive here. We want always A then B. Whenever A comes, we should see the other A also, right. So, what should we do? The usual trick is that we just combine the two A's together into one A. We can say A dash, right, and wherever so now instead of a multiset of this sort A comma B comma C comma D, we would rather have a multiset of this sort A dash B comma B C comma C D comma D, right. So, and now we will permute this one, and whenever A dash appears we will replace with 2 A's. That means the A is visited consecutively, right, that is what. Now, this will give you the count, but this multiset is what we in our notation it will be 1 A dash, 2 B and 2 C and 2 D, right. The cardinality of the multiset is 1 plus 2 plus 2 plus 2, that is 7, cardinality S equal to, this is n, and now we have k equal to 4 because there are 4 types, and n1 equal to 1 because here it is only one type, n2 equal to n3 equal to n4 equal to 2. We can easily find the answer for the number of permutations of this sort, that 7 factorial divided by 1 factorial into 2 factorial into 2 factorial into 2 factorial. This is the total number of possible ways to visit the factories such that the factory A is always visited on consecutive days. Now, this is not what we want is the other thing, namely the factory A is never visited on consecutive days. So, therefore, the total number which was 8 factorial divided by 2 factorial raised to 4, right, minus 7 factorial divided by 2 factorial raised to 3 will give you the answer. I am not calculating it. So, this will be the answer. So, here we have made use of several notions that we have studied already. So, the namely subtraction principle we have used, and this notion of permutation of a multiset we have used, right, and that idea of combining two A's into one A. So, something which is very useful, which is like instead of always how will you express that idea that two A's should come together, right. One way is to just say that instead of two A's we just call A dash, and after getting the permutations A dash is substituted by two A's, right. So, this is a useful trick which you can remember. Now, we will look at the next example. Yeah, this is a very usual question. The number of permutations of the letters in the word Mississippi. How many ways you can write the letters in the word so Mississippi. See, the point here is if all the letters were different, you would have got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11 factorial things, 11 factorial possible permutations of this thing. For instance, a word of this sort A, B, C, D, E, F, G, H, right, 1, 2, 3, 4, 5, 6, 7, 8, I, J, K is a 11 letter word. So, if somebody asks you how many ways you can permute it, I mean how many words you can make out of this thing by reordering them, it would have been easy, right, we know already that. But here the difficulty is that several letters are repeating. So, this is not just 11 letters, this is not a set of 11 letters, this is a multi-set of 11 letters. So, the multi-set is like this, there is one M and 4 I's, and then we have 4 S's, and then we have 2 P's, This is the multiset. 1 M, 4 I, 4 S, 2 P, and that is it. Total 11, 8 plus 2 plus 1, 11. So, the cardinality of the multiset N is equal to 11. Now, we have 4 types K equal to 4. So, these types are M, I, S and P, these are the types, and then each one, the type 1, that is 1, N1 equal to 1, N2 is equal to 4, N3 equal to 4, N4 equal to 2. We know the answer now. We just have to permute this multiset, that is what it is asking. We do not have to think much, that is 11 factorial divided by 1 factorial into 4 factorial into 4 factorial into 2 factorial, right. And the next question. So, we will have a different view of this problem now. So, the this permutation of the multiset was one view we had. We had a multiset containing n things in it. I mean, adding together all the repetitions, the cardinality of the multiset is n, and there are k type of things in it, objects are of k types, and then each type, the first type is n1, second type is n2, the last k the type is nk, and how many ways you can order these objects of the multiset in a list. With the entire multiset, how many ways you can permute? This was the question. Or another way, we just told we want n objects to be listed, that is what, right, instead of using the multi set terminology. Now, we say we have n objects and we have to place them. These n objects are now different objects, right, different objects, maybe distinguishable objects we want to place them in k labeled boxes, means boxes are also distinguishable. For instance, the first box you can put, second, I mean you can see the boxes have a number on them, or maybe their boxes are of different colors, we can immediately distinguish a box from another. So, boxes are B1, B2, Bk, but the restriction is that the ith box should contain n I objects. After you distribute it, ith box should contain n I objects. So, this is looks like a different problem. This so we in combinatorics classes we always talk of balls and bins problem. So, here we are talking about n distinguishable balls, that means those balls, each ball we can identify one from the other, right, and the bins are also distinguishable. We can say that so there is this n buckets or bins, and we can identify one from the other. The key thing here is that the distribution, I mean how many should go to the ith box is given predefined. Now, how many ways you can put them? The total number is n1 plus n2 plus nk, right. How many ways you can do this thing? This turns out to be the same number. So, actually the one of the proof was doing this thing. For instance, what was we doing in the first proof? We kept n positions in the first position, second position up to n positions, and then these n positions we were allotting to these n positions we were allotting to each type, right. We are saying that the first type has to get n1 positions. So, n1 of them should go to the first type, that means first types will go and occupy those n1 positions. How many ways you can select it? That can be done in n choose n1 ways. Now, that n1 positions are gone, now n minus n1 positions are left, and this out of this n minus n1 positions, n2 should be given to type 2, or in other words n2 of them should go to bin B2. That is the kind of the type is like my now matching with the boxes, label boxes, k types, right, and this actually the positions are the distinguishable objects here, and they are going to n1, n2, nk, something like that, right, the numbers, right. So, this is therefore, this is almost the same proof, just that once we understand the correspondence, there is nothing big here. So, it is immediate. So, let us see. So, I will just describe. The question here is we have n objects, all can be distinguished, right, and this is actually n1 plus n2 plus nk. Now, these objects, these n objects are to be placed into see the B1, B2, Bk boxes, this many different boxes we have to place, right. But the B1 should get n1 of them, B2 should get n2 of them, and Bk should get nk of them. That is the main restriction. How will you do that? So, out of the n objects you select n1 things which should be given to box B1. That can be done n choose n1 ways, right. And the remaining things n minus n1, from that you choose n2 things which should be given to box number 2, and from the remaining things, that means n minus n1 minus n2 remaining things are there. Out of that you can choose n3 objects, and which can be given to the remaining objects, and like that we can do n minus n1 minus n2 minus, finally if the last box when you take this will be nk minus 1. We have to select k objects. Actually this might have become nk now, right. So, we are just selecting all of them, that is all, because that is it, that should be given to the kth box. And we have to multiply these things together, because this is the number of ways we can select that first n1 things to the n1 things to be given to the first box, and from the remaining things this is the total possible number of ways to select n2 things to be given to the second box. For any selection of n1 things to be given to the first box, you can combine it with a selection of n2 things to be given to the second box. Therefore, that is multiplication. This is a product rule we are applying, and therefore, we just can multiply them out. When you multiply them out, we can just expand this is n factorial by n1 factorial into n minus n1 factorial into here n minus n1 factorial divided by n2 factorial into n minus n1 minus n2 factorial into n minus n1 minus n2 factorial divided by n3 factorial into n minus n2 minus n3 minus n minus n1 minus n2 minus minus n3 factorial and so on, right. This will go on like that, and you know this will telescope, this will cut like this, right. And finally, you know what will remember this one, what will remain, this this will remain in the numerator, that is n factorial, and in the numerator, in the denominator we have this and this and this and so on, right. That is n1 factorial, n2 factorial and nk factorial. You can just work it out yourself, does not matter, this is just manipulation. So, this is what, this is exactly the same number. As I told you, as you can see from the proof, it is the same thing, same proof that we have done. Actually, just that this n objects in the earlier proof was n positions, and this boxes, label boxes is actually the types, right. The first type correspond to first box, second type correspond to second box, and third type correspond to third box, and kth type correspond to kth box. There we are telling that this, say the first type occupied n1 positions. Now, we are saying n1 objects are selected and given to the first box, put in the first box, like that, that is the only difference. So, therefore, it is the same number, it is that it is told in a different way, right. But still you can notice that the problems can appear in any ways. So, you have to interpret it in the correct way. So, this is one model which we can keep in mind. There are boxes, there are balls, right. Sometimes the balls, so in some problems the balls may be all identical, sometimes the boxes may be all identical. So, in this problem balls are also distinct, I mean all the balls are different, I mean you can distinguish one ball from another. The boxes are also different, you can distinguish one box from another box. So, the speciality here is that here the number of things which should go to the ith box, a specific box, how many things should go is already given to us, right. In some cases it may not be given, we may have to work harder in that case. So, it may be just say that okay, how many ways you can split it, that may be the question. So, this it can, so we will keep discussing about these balls and bins problems all through this course, because that is something which you can keep in mind. And then of course, like in the pigeonhole principle, the difficulty is not remembering the answer to a certain type of balls and bins problem, but rather identifying when a new problem comes, identifying that this is this kind of balls and bins problem. Most of the time you won't know what are the balls, what are the bins, and that is the difficulty. Like in the pigeonhole principle, we were saying that how will I identify which are the pigeons and which are the holes. That's most of the time that is the difficult task. Once you identify the pigeons and holes, then application of the pigeonhole principle was almost trivial, right. So, but most of the time to decide which should be the pigeons and which should be the holes was different. Similarly, here to decide which should be the balls and which should be the bins will be difficult. Here there is this added complication that there are many problems we have to remember. In some cases the balls will not have numbers, that means they will not be distinguishable. In some cases the bins will not have numbers, sometimes both of them have numbers, sometimes how many should go to a ball is given, sometimes it is not given. So, we have to remember a lot of things, but at the same time, but remembering may not be very difficult, but more difficult is to identify which problem is relevant to which situation when a new situation comes. But anyway, when you get more and more familiar, one gets more comfortable with it. So, now the so for instance, one can see to illustrate the point, for instance, you can take this simple example. Let us take A, B, C, D. There are these 4 objects. Now, these are all different, right, A, B, C, D, right, one can distinguish from one another. Now, we say I want to put them in 2 boxes. So, one is 2 boxes, right. How many ways you can put? Suppose these boxes are distinguishable, then I can do it in 6 ways. What all ways? Because in this I can ask in this green ball, right, I can put any of the 2 things, because once you put 2 things in this, remaining 2 will go. It means what I want to do is this green box should get 2 things, right, and this red box should get 2 things, right. So, here our problem says n1 is equal to 2. So, our B1 is the blue box and our B2 is the red box, and this n2 is also equal to 2, n1 equal to n2 equal to 2. It is a case of n1 equal to n2 equal to 2. Now, you just have to decide what we should put here, right. The other 2 will go automatically there, and we know that this can be done in 4 choose 2 ways, right. So, AB can be put here, or CD can be put here, or BC can be put here, or AD can be put here. There are 6 ways to put it, right. So, 4 choose 2 ways. Out of 4 things, you just have to select 2 and the remaining will go there in the red. But you see, suppose the boxes, both the boxes were blue, that red color was not there, then there are no 6 possible ways are not there. Why? Because if I put AB here and CD here, and another this thing, I could have put CD here and AB here, both are same, because how will you distinguish between these 2 configurations? I am just drawing it again. So, this is AB and this is CD, and here it is AB CD, right. Actually, it is just that we just put this box here, put this box here, they are not distinguishable. So, you may even think that somebody just shuffled the boxes, right. So, but earlier we were counting this as 2 different things. So, we have to divide now by that answer 6 by 2. So, we have only 3 possibilities now. Any configuration, that configuration earlier was counted twice. So, now it is, sorry, for any configuration here it is counted twice. So, therefore, we naturally will tend to ask the other question. Suppose this suppose I now get rid of the labels from the box, that means the boxes are made indistinguishable, they cannot be differentiated. So, all boxes are the same color or they look same. Then how many ways are there? So, one special case only we consider, the case when n1 equal to n2 equal to n3 equal to nk, all k boxes has to get equal number, right, this n by k, right. Here the boxes we are making same, k boxes, and the numbers which should go into them, they are all equal, because otherwise again there will be some difference. And now how many ways you can do? It is clear that any order if you give, because some we had put something here, some objects here, some objects here, some objects here, some numbers were, some n1 objects had gone here and 2 objects were gone here. And now any permutation of this thing. So, this k factorial ways I can rearrange them, this comes here, this comes here. So, this rearrange the bins themselves, that means we can rearrange the boxes themselves in k factorial ways, but each of this rearrangement was counted once correspond with the same objects in each box, and with one reshuffling of the boxes it was counted as a new entity in the previous counting. So, now, but then for this we know that now this reshuffling of the boxes does not matter, shuffling of the boxes does not matter, k factorial shuffling will not affect it, only when we change the internal contents of the boxes, then only we have to worry, right. So, therefore, the total number, again we can use division principle here to infer that the total number of ways you can place n objects, n balls, n distinguishable balls in k unlabeled boxes. Unlabeled means we cannot recognize the box, one box from another, such that each box should get the same amount, is this one n1 factorial. So, it's maybe we can set n by k factorial, n by k is an integer now, right, n by k factorial all raised to k, right. So, the reason is that this is again just division principle. We are seeing that when it is the boxes are assumed to be undistinguishable, like each arrangement here, valid arrangement here would have given rise to k factorial different arrangements in the earlier situation. That means, earlier situation was when the boxes were distinguishable. You can just assume that the boxes are placed in a row, and then now the objects are placed inside the boxes. Now, without changing the content of the boxes, we just replace the boxes, the order of the boxes are changed, right. That is the same thing for in the second case where the boxes are unlabeled, but different things in the case when boxes are labeled. Therefore, division principle says that okay, on one side we have this unlabeled box case, the other case we have the labeled box case. From the labeled box case to the unlabeled box case, we can define a function, like the function is defined like if this arrangement correspond to this arrangement of the other case, then of course we map it with that, and it is definitely a D2 function where d is equal to n by k factorial, n by k being the number of things which we give into that to the square, right, to the k, right. So, okay, so that is the number of partitions will be equal to that. So, this is one different case we can remember. Now, what is the next question we are considering is this. So, this is a question where about the chessboard, it's about the rooks which we use, which is a piece in a chess game, right. So, interesting question. This is, so we consider an 8 by 8 chessboard, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, and 7, 8. So, the rook means, suppose if I place a rook, then this can attack anything on this row, anything on this column also. So, you are not now a non-attacking configuration means you cannot place another rook here, right. This is not allowed. One rook is placed here, another rook is not. So, you can place another rook, say maybe here, that is okay. But once you place this guy here, this rook here, so it will attack anything which is placed here or here, right. Now, in the any other rook, if you want to place, maybe you can place it say here, yeah, because neither this attacks, this attacks. But then once this you place this will attack this row and this row, right. Now, if you want to place another one, how many rooks you can place like this? Of course, you cannot place more than 8, because there are only 8 rows, and if you place 9 by pigeonhole principle on the same row, 2 rooks have come and then they are attacking each other. Can you place 8? It is not very difficult to show a configuration where you can place 8. But what is this problem? The question is how many ways you can place 8 rooks on the chessboard in non-attacking configuration in such a way that they do not attack each other. So, this question, first of all, we notice that in each row we can only place one rook. So, this is first row, this is first row, this is second row, this is third row, this is fourth row, this is fifth row, this is sixth, seventh, eighth. In each row we can place one rook. So, if you want to describe the positions of the rooks, we can say in the first row this column, which is the column. So, I can just say J1th column, right, or maybe I can say column number C1, 1 C1. Similarly, in the second row, now in the first row you can only place one rook. So, we just have to specify the column number there. Here it was 1 itself, right. So, something like that. And the second row you can specify the column number C2. Maybe here it can be here. So, that is 1, 2, 3, 4, 5. So, this can be 5. In the third row, it is C3, column number C3. Here we have placed it as third column, right, third column. This is 3. Like that, in the fourth row we have C4, column number 4, and so on. 8th row we have C5. You see that we could have you can easily notice that it is the function that is being written here, because see, function from 8 to 8, right, this is some function from 8 to 8. Why it is a function? Because for each of these 8 numbers 1, 2, 3, 4 up to 8, we have a value assigned to it, right. So, f of 1 is equal to C1, f of 2 is equal to C2, and f of 8 is equal to C3. So, for function, another thing we want is that everything has one value, and also everything has only one value. Oh, that is also true here, right. We know that in a given row, ith row, we cannot have more than one rook. So, it is only it is the function that rook, the position of the rooks are specifying a function. See, any configuration which is valid will define a function. What kind of a function is this? The function, see, for instance, if this function is essentially as if it is plotted here, right. So, looking from 1, so this is plotted here. So, the function value is plotted here. This is like height 1, 2, 3, 4, 5, 6. This is the y axis, right. This is the x axis, something like that. So, right, 4, this 2, 3, 3, and 1, 1, 2, 5, like that. The interesting thing is that given an I and given a j, f of I and f of j, can they be equal? No, because in that case, say suppose f of I equal to f of j is equal to say 7. That means in the 7th column you will see 2 rooks placed, maybe something like this, which is not allowed, because then these rooks will be attacking each other. So this is also not true. Then what kind of function is this? It is a function from 8 this to this, 8 to 8, right? 1 2 3 8 to 1 2 3 up to 8, and no two numbers, no number is getting mapped to two different numbers. No two different numbers are getting mapped to the same number. That means it is a bijection. It is a bijection. It is a one-to-one correspondence. It is a bijection, or say we say one-to-one correspondence. One-to-one correspondence means it is a function from a set to set for anything, for any right function from A to B, right. We will say any member in B has exactly one pre-image. It has a pre-image, it has exactly one pre-image, it does not have more than one pre-image. That is what is happening here. The chessboard situation, we see that if you take any I, so it has an image, okay, that is why it is a function, and if you take any column, that has only one rook sitting there, therefore that will define its pre-image uniquely, right. So therefore it is a bijection. Actually any bijection from 8 to 8 would give a valid chess position. Why? Because if it is a bijection, that means I throw, if you look, f of I is uniquely defined, only one value is there, so a rook is sitting there, and any column, if you consider the jth column, you cannot have two rooks sitting in the column, because if they were two, then that means that two different i's, I say I1 and I2, are such that f of I1 is equal to f of I2 is equal to j, right. Two different rows are getting the rook on the same column number, right. So that is not allowed. So the same rooks on the column number, that means this bijection says that it is not allowed, right, because the same thing will not have two different pre-images, bijection. So the bijections from 8 to 8 corresponds to the number of the rook arrangement of 8 rooks on the 8 by 8 chessboard, such that they do not attack each other, pairwise non-attacking position. And conversely, that means if you have a non-attacking configuration of 8 rooks on the chessboard, that would correspond to a bijection from 8 to 8. So we have this one-to-one, I mean, so okay, this is a bijective proof that this one and the same, right. So 8 to 8. We can of course generalize it to an n by n chessboard, right, because the same argument says that if you have an n by n chessboard, and then n rooks are to be placed in a non-attacking configuration, any such configuration will correspond to a bijection from n to n, right, n to n, right, and reversely any bijection would give us a configuration of n rooks on the chessboard such that they do not attack each other, right. So therefore we are actually counting the number of bijections, and the number of bijections is easy to count. What is that? For instance, f of 1, how many ways you can fix a value for f of 1? There are, so we are telling about f number of bijection from n to n, right. So there are n possible ways to fix it, because there are n values here, but the only thing is, once you fix a value for f of 1, f of 2 can be assigned a value only from the remaining n minus 1 things. So n into n minus 1 possibilities for fixing values to f of 1 and f of 2. Now f of 3 can take values from the remaining n minus 2 things. So there are n minus 2 possibilities. and so on. That means by the time we fix value for f of n also, we get this number n factorial, right. There are n factorial possible. So, this tells us that probably this has some relation with permutations also. Yes, it is, because you can see the bijection you can draw like this 1, 2, 3, 4 n. So, you 2, 3, 4, 5, 6 n. So, this 1 is given this value, 2 is given this value, 3 is given this value, and for something like this, some figure. I mean, I can draw this, sorry, not like this, it is a bijection. So, yeah, such that each object here gets a unique object here. So, this is the image of this, this is the pre-image of this thing. If you look from here, there is only one pre-image for each of them, and everything gets a pre-image. That is the picture of a bijection will look like this. As you mentioned, this corresponds to some root configurations, right, non-attacking root configurations, and this is actually n factorial. This tells us that maybe this has something to do with permutations also. Of course, it has something to do with, for instance, if you write f of 1 this like this, f of 1, f of 2 up to f of n in a sequence, how will it look like? So, f of 1 is 4, right, f of 2 is 1, f of 3 is n, and like that. Nothing will repeat, because these are bijections, right. For once f of I writes some value here, no other f of I dash can write the same value, right. So, therefore, this will be a permutation the way it is written, right. Each bijection will give us a different permutation, and reversely, if I have a permutation, like for instance, this is a permutation 2, 5, 6, 8, 9. I can say that 2 is f of 1, 5 is f of 2, and this is f of 3. Clearly, I can define a bijection using this, looking at this permutation, right. So, there is a one-to-one correspondence between the permutations and bijections also. So, essentially it is the permutations, the bijections from n to n is the number of, it correspond to the permutations of n. So, that is, therefore, there is no surprise that it is n factorial. So, we see that this n factorial correspond to the number of permutations of the set n, and also it is the number of bijections from the set n to n, number of bijections from set n to n, and then it is the number of non-attacking rook configurations, n rooks on a n by n chessboard, right. And now we will ask a new question. I mean, for instance, so we just set up this rook problem to ask the the following question. So, let us see, this is the question we want to ask. Suppose if all the rooks are colored differently, and then how many configurations are there? What do we mean by this thing? For instance, looking back at our problem, I just draw a small chessboard, right. It is not necessarily 8 by 8, it is just say n by n chessboard, right. So, now this is n by n. Now, I am saying that I am placing a rook, say one here, say one here, one here. This is a non-attacking configuration, right. So, maybe we can put a little more. Yeah, one here, yeah, maybe this is not necessary. Right. So, this is a non-attacking configuration of this around. But now we see, suppose this rook was green, this was red, and this was blue, and this was yellow, and this was a brown, and this was a black. These are all, you can identify which rooks, and then if I had placed this rook here, and see, for instance, if I had placed this blue rook here, sorry, blue rook here, and my red rook here, it would be different. Or if I had brought this yellow guy and placed it here, right, and put that black rook here. So, let us put that black rook here, that is different. So, black rook here. Yeah, that will be different, right. So, how many ways now you can do? Of course, we have basically 8 factorial ways to place the rooks. Now, for one placement of the rooks, we can play with these colors. I mean, this is like for this position, this is the first position, first position, second position, third position, fourth position, because in every row we have only one position. Say this is the first, this is the second, this is the third, this is the fourth. Whatever you see on the first position, first row is the first rook, second row what you see is the second rook, and so on. So, now you can assign the colors to that, right, from you can say from 1 to n, right. We have a mapping from the color set colors. There are how many colors? There are 8 colors, suppose. All the rooks are different colors. So, which color should go to that position? That is what we are asking. First row rook, which color should get? So, this is essentially again the bijections, all possible bijections will give you that. So, there are 8 factorial ways to do this thing, 8 factorial ways to position the rooks. Now, for one positioning we can assign the colors. Assign the colors means we can put the, we can decide to put which color here and which color here, which color here, that will be another 8 factorial. So, that is either we can say that we are permuting the colors here, all the 8 colors in any ways, right. So, we read from here to here, it is an ordering of the colors, right, 8 colors, or we can say that it is a bijection from 1 to n, the set 1 to n to the set of colors, right. So, f of 1 is a particular color, f of 2 is a, f of I is a particular color. F of I means the color of the rook which appears on the ith row. There is only one rook which appears on the ith row, and that can be any color, right. So, there are again 8 factorial ways. So, it is essentially 8 factorial square with a number of possible arrangements. Now, the next question is slightly, I mean, again sophisticate the question. Suppose now we say that, I mean, of course, we considered initially we considered a situation where all the colors were same, actually the rooks were indistinguishable. In the second question we considered the case where all the rooks were of different color, that means any 2 rooks can be distinguished from each other. Now, we say there is 1 red rook, 2 blue rooks and 4 yellow rooks. That means some of them are distinguishable, means 2 blue rooks, between them we cannot differentiate, right, with just 2 blue rooks how will you know which one is which. But between a red rook and a blue rook definitely you can distinguish. How many ways you can do this thing, right. Again the basically the arrangement of the rooks, I mean first arrangement of the rooks, this in this row which column, I mean the first row which column should I select for the rook to be placed, the second row which column should be placed, that I can again do in 8 factorial ways as we discussed earlier. The colors does not make any difference there, but once we decide a position, now the colors make a difference. It is essentially the colors, this is a multi-set. Now, earlier it was all different colors, one red, one blue, one green, like that. Now, it is 1 red, 2 blues and 4 yellows, right. This is what we told, right, in the problem. Yeah, 2 blues and 4 yellows, and total number n is actually 8, 4 plus 2, sorry, actually yeah, so I took, yeah, it should be, say let us say 2 red rooks, it should be 2 red rooks, let us say 2 red rooks, 2 blue rooks total, so that n becomes 8. So, we consider 8 by 8 chessboard, that is why I wrote 8 factorial, right. So, now how many ways we can assign the colors, in the sense that the deciding which colored rook, which a rook of which color should go to the first row, which rook of which color should go to the second row, rook of which color should go to the third row. This is essentially a permutation of the colors, because the row 1, row 2 is, you can assign the first row got blue color, the second row got the second row got the red colored rook, the third row got the yellow colored rook, fourth row again got the yellow colored rook. So, therefore, this is a permutation of colors, just that some colors are repeating. So, it is a permutation of the multi-set, this multi-set, right. And we know how many ways we can do that, because 8, that is 8 factorial, because n equal to 8 and n 1 equal to 2, n 2 is equal to 2 and n 3 equal to 4, that is 2 factorial into 2 factorial into 2 factorial. We have to multiply this with this, right, because basically we have 8 factorial placements. When we forget about the colors, we have 8 factorial permutations. For each 8 factorial non-attacking configurations, with colors we can make this many changes. I mean, for placing the rooks on the same position, but we can change the colors. I mean, colors means we have to decide which color should go to which row in this many ways, 8 factorial by 2 factorial. This is what the final thing we taught, the permutation of the multi-sets, right. And naturally we can very easily generalize it to the n case. Suppose there is an n by n chessboard and there are n rooks placed in a non-attacking configuration. Of course, we can do it in n factorial ways, as we have already argued out. Now, there are n 1 rooks of color 1, C1 color, right, and n 2 rooks of color 2, n 3 rooks of color 3 and n k rooks of color Ck, right, color k. So, such that if you add up these things, these numbers, these are repetition numbers, right, this is n k will give you n. Of course, there are n rooks, right, they should add up to n. Now, how many ways you can do this thing? Of course, basic arrangement is n factorial, and for given one arrangement, the colors can be assigned, or means you can decide which rook of which color should go to which row in n factorial by n 1 factorial into n 2 factorial into n k factorial ways, because this is the number of permutations of that multi-set, right, and this is equal to n factorial square divided by n 1 factorial into n 2 factorial into n k factorial. This is what. So, this is the number of ways to place n rooks on an n by n chessboard in a non-attacking configuration when n 1 rooks are of a certain color, n 2 rooks of a certain different color, and n k rooks are of a kth type of color, kth color, right. So, we will continue in the next class. Thank you.